Today we'll start a totally different chapter in our course where um, we don't concern ourselves with privacy, authenticity, and the previous notions that we've seen that cryptography is supposed to deal with. Instead, we're going to introduce coding theory. So the whole point of coding theory is that we assume messages, we'll see later that they're in fact, we will call them code words, are transmitted through a noisy channel. And through this channel, they receive some noise that we call E in this picture. And we are, so instead of concerning ourselves about privacy, this time we're concerned about figuring out how to detect that errors were introduced during the transmission, and if so, figure out a way to correct those errors, which is really the ultimate goal for error correcting codes. So the first obvious way to transmit information through a noisy channel is to introduce redundancy. So for example, if you want to transmit either 0 or 1 through a noisy channel, then instead you may transmit a 0, 0, 0 instead of a 0, and a triple of 1s if you meant to send 1. Then on the other end of the communication channel, you may receive either, so triplet 0 if there was no error, or 0, 0, 1, 1, 0, sorry, 0, 1, 0, or 1, 0, 0. And then in that case, if you receive one of those messages, then you will declare that a 0 was intended as the message, while if you receive triple of 1 or 0, 1, 1, 1, 1, 0, or 1, 0, 1, then you will declare that these were the intended message was in fact a 1. Okay, so this way you can correct up to one error. So let's see what formal definition we have and how they fit what we just saw for the repetition code, which is introducing the naive way of introducing redundancy. So first of all, unsurprisingly, a code is a set of code words, which begs the question, what are the code words? Well, in the case of the repetition code that we just saw previously in the previous slide, then there are two code words. One is the triple of zeros and one is the triple of ones. Okay, and these are the ones that are being transmitted through the communication channel. Okay, now the code words, what are they formally? They're strings of symbols on an alphabet. So here we have two more notions that we have to define. So the alphabet, is going to be a set of symbols, of course. So for example, here our alphabet is 0 and 1. Okay, and M is the length of the code. So whenever you have code words of length M, then length is the code. And if Q, which is the size of the alphabet, if that is the size of the alphabet, then we'll say that C is a Q area code. And in the case of C repetition, so length is 3, while Q equals 2, because the alphabet here, in our case, is just the set 0, 1. So in that case, Q equals 2, of course. And we're talking about a 2-area code, which really you should call a binary code. And that's it. So we see how our previous construction actually fits the formalism of coding theory. So before we talk about detecting and correcting errors, we need to have some form of distance between elements that are words on the alphabet where where the code lives. Basically, we need to quantify the impact of errors, and to do that, we have to see the errors that occur during transmission as drifting from one code word to some element in A to the M in a way that we should be able to quantify. Okay, so the Hamming distance, of course, is not just defined between code words, but really between elements, between words on the alphabet A, and the distance is simply the number of indices where the two words differ. Okay, So for example, the Hamming distance between 0, 1, 0 and 1, 1, 0 is going to be 1 because they differ only on the first coordinate. Okay. Now be careful, the Hamming distance is not the Euclidean distance. Sometimes it can be tempting to, because the two notions are very similar, except for the fact that each coordinate, if for example the difference between a 0 and a 1 is the same as the difference between a 0 and a 2 or 0 and a 3, and I could even use symbols that are not even numbers. No, that would of course be less confusing, but if I'm using numbers, it doesn't matter that the two symbols are more different. They're just they're all the same. As soon as they're different, it counts for 1 in the Hamming distance. And now the code itself can have a Hamming distance. That's a very important property to quantify our ability to correct and detect transmission errors. And we call that it's the minimum for all u and v's in C, where u is different than the v of the distance between u and v. So of course, distance between u and u is 0, but that doesn't count. So u and v have to be different. So what is the distance of C-rep? Well, C-rep, remember, there are only two u and v. So you have u equals 0, 0, 0, and v equals 1, 1, 1. And these are the only two different code words. And then you have, of course, that the distance between u and v equals 3. And that shall be the distance of C-rep. Okay? So now let's see how distance of the code pertains to our ability to detect errors. So here is what we can say. We can detect the presence of a transmission error if the number S of errors is less than the distance of the code minus 1. Okay, so or the distance of the code has to be greater than S plus 1. So in that case, how do you decide if you've if there was a transmission error? Well, if you receive a code word, you know in that case that it was the code word that was sent through the communication channel. Now, if you don't receive a code word, then you know, of course, that there was a mistake. The only thing that we have to rule out during the proof of this proposition is the potential for sending a code word and then having so many transmission errors during through the transmission channel that we drift onto a different legitimate code word. So you send C1, and on the other side of the communication channel you get C2, and now you receive a code word and you're wondering, well, was this really what was sent, or is it just that we had so many errors that we jumped from one code word to the other. So here's the code word that you originally sent. So let's call it C. And we receive C plus some error, okay? And that distance is at most S, okay? Now, here's the thing. If R, the received word, is a code word, okay, then you have that the distance between, so if that was to be a code word, then you'd have that the distance between those two code words is less than distance of the code, right? Because we just said that distance of the code is strictly greater than S. And therefore, by definition of the distance being the minimum of the distance between two different code words, then it would have to be that C prime and C are the same, okay? And otherwise, well, you see that in that case, you see the nearest code word to C has got to be longer, okay? So you see that if the nearest code word different than C, of course, here, we could call it, C0, and it's got to be that it's outside of the sphere of radius S, okay? So there is no other code word inside the sphere than a C itself, okay? So whatever you receive, it's either here, okay, and it's not a code word, or it's got to be If it is a code word, then it's got to be C. Okay? Okay, and of course, yeah, you know when you make a transmission error trivially. Now, even more interestingly, how do we correct errors? Okay, and that's very important because knowing that you received garbage is one thing, but knowing what was the intended message is even better. Unsurprisingly, the condition on the distance of the code is going to be stronger, meaning that if you want to correct T transmission errors, so T is the number of errors that you want to correct, then the condition between T and the distance of the code has got to be that the distance is greater than 2T plus 1. Okay, so in this case, you can see that if you can if you can detect S errors and correct T errors, in general, T is going to be less than S. Okay. Now let's see why we have this particular condition here. So here again, assume you received C. Okay, and it's drifted to C plus E. Okay. Now we want to prove that there can be only one code word at distance T from the received message. Okay, so this is what we receive, and there is a sphere. So this is, I should say, it's less than T. Okay, and there is a sphere of radius T centered around the received message here, and we want to argue that there is only one code word. Okay, and if there's only one such code word, then clearly it's got to be the one that was sent. Okay, so by way of contradiction, suppose that there are two different code words, C1 and C2, okay, and they're both in the same sphere of radius T. Okay, and then so they're both so at distance R, less than R. Okay, what happens with triangular inequality is that the distance between those two code words has got to be less than 2T. Okay, but remember, we just assumed that the distance of the code was greater or equal to 2T plus 1, so strictly greater than 2T. Okay, so the distance of those two between those two code words is less than the distance of the code, which means necessarily they have to be equal. Okay, so you cannot have two different code words in that sphere of radius T. Okay, so the decoding, of course, is to look at the sphere and pick the one code word, the one and unique code word that was in the sphere. Okay, and that's got to be the intended message, if of course you believe that your transmission channel did not induce more than T errors. Okay, so example of those formulas. You have the repetition code, whose distance I remind you that this distance we calculated to be 3. So how many errors do we detect? Well, we have that the distance of C is greater than 2 plus 1, okay? And in that case, so that would be the S, so we can detect 2 errors. Okay, but now how many errors can we correct? Well, we have distance of C is greater than 2 times 1 plus 1. So that 1 would be T here. And so we correct only 1. And that makes sense, right? It seems logical that it's easier to just merely detect an error than correct it. Now, let's finish this lecture with sort of a quantification of one way of quantifying efficiency. I shouldn't say maybe efficiency, but more quantifying the redundancy that we introduce. Okay, we can bump up the distance of the code arbitrarily to make it arbitrarily large. If I take the repetition code, instead of having m equals 3, I can have m equals an arbitrarily large number. So I could cook up a code that will allow me to detect and correct an arbitrarily large number of errors. Okay, But then, of course, it would come at a price of a lot of redundancy. So we need to quantify that redundancy, and this notion comes with the notion of rate. So we call an MMD code is when it has length M, capital M code words, and distance D. Okay, and let still Q be the cardinality of the alphabet. The rate of the code is the log and base Q. So let me remind you that Q still is the cardinality of the alphabet. The rate of the code is the value log and base Q of M over small m. Okay, so what does it mean? Well, what it means first, before we calculate that of Crep, what it means is that we have here this value, okay? It's a value that would be essentially, so we would have the number of words that we can make out of an alphabet of length of size q is q to the m. Okay, so without redundancy, you would have exactly q to the m code words. Okay, but in fact, you sacrifice, by adding redundancy, in fact, you sacrifice some of those potential words. You cannot, you say, for example, like maybe half of those words are going to be code words. Okay, so you adding redundancy means that, for example, that means that essentially you will not use the entire range of the possible words of length m on the alphabet A that has size q. Okay, but if you had no redundancy, well, then you would have a rate that would be exactly 1. Okay, so rate without redundancy here, you would have log q over m would be essentially m over m, which is equal 1. So you will never exceed a rate of 1, but in general, it will be strictly less than 1. So let's see in an example, Crep. For Crep, what do we have? We have q equals 2. And then we have capital M equals 2 as well, okay? And M, which is the length of our code this time, is 3, okay? So the rate equals the log in base 2 of 2 over 3, which is 1 over 3, okay? And that is a that shows that we have redundancy. In a way, you could think of it as saying that each character is only 1/3 of your information. Okay, you could get away without, if you were not introducing redundancy, then you would have only two. You would have only 2 code words basically. I mean, you could have one character, okay, a 0 and a 1 to have a, and so m would be equal to 1. And that would give you a rate of 1. Okay, the more you introduce redundancy in the repetition code, if I was with m equals 5 or m equals 7, or if the larger I make m, the more redundancy I introduce, and the smaller the rate is going to be. Now let's finish with a bound on the rate. Okay, so we can actually give for a query MMD code, we can claim, in fact, that m, number of code words, is bounded by q to the m minus d plus 1, which automatically gives us an upper bound on the rate. So it basically says you will never, with those parameters, never exceed a certain rate. So how to prove this? For each code, we define sort of like a tail of each code word. Sorry, we define a tail of these code words by dropping the first d-1 coordinates. Okay, so you take the d-1 coordinates at the beginning, and you just basically cross them out, and that gives you a code word, sorry, a word, I should say, of length m minus d plus 1. Okay, and it turns out, if we assume the distance to be d, then if 2 different words, C1 and C2, are code words, So by definition of distance, they must differ on at least d coordinates. And if I've dropped the first d minus 1 coordinates, then their tails must differ on at least one coordinate, maybe more, but at the very least, if C1 and C2, their distance at least d, then and that could be that they're all the coordinates on which they differ, you know, they might be all at the beginning of the word, but by dropping d minus 1, we're still left with at least one coordinate that differs on the last m minus d plus 1 coordinates. So what it means is that those different tails, I have only a q to the m minus d plus 1 choices of such tails, such words of m minus length m minus d plus 1. So that means that there cannot be more than q to the m minus d plus 1 code word.